In this video, we're going to look at an advanced problem for harmonic motion. We've got a 40-gram mass vibrating in simple harmonic motion at the end of a spring. The amplitude of the motion is 5 centimeters and the period is 3.7 seconds. Find the following variables. The first one we want to find is the frequency. Then we want to find the spring constant, the internal energy of the system. How are we going to do that? Then we want to find the maximum velocity of the mass, the position at time equals 1.5 seconds, and the acceleration when time equals 1.5 seconds. So this is going to be a challenging problem. Right off the bat, let's draw out a model. So I've got a spring connected to a mass. That mass is 40 grams, and it's oscillating back and forth. So let's draw that as well. So the amplitude of the motion is 5 centimeters. That means from this point right here to this point right here, that change in x will be equal to my amplitude, which will be 5 centimeters. So this is our model for this. And I want to know, first off, what's the frequency of this travel? That should be pretty easy. The frequency should be pretty easy because period is equal to 1 over frequency. The spring constant, how am I going to find that? Well, I know it's got a constant, and I know that we have certain relationships, like the relationship in the period. So I can use this equation to find my K value. The internal energy of the system, how can I find that? In order to find that, I need to make use of the energy equations. I either need to know the maximum velocity, which D is asking for that, so clearly I don't know, or I need to know the maximum potential energy. And the potential energy here is going to be the potential spring energy. So it's going to be U, which is US, which is going to be 1/2 kx squared, which that's not too hard to find. So at my maximum displacement, which will be when the displacement is equal to the amplitude, then I'll be able to find my maximum potential energy, which will tell me the internal energy of this system. So the system will have that energy moving back and forth. Then once I know that, I can find the maximum velocity of the mass, because that maximum velocity will be when the potential energy is 0, making the kinetic energy equal to the total internal energy of the system. So K will equal 1/2 mv squared. And then the position at t equals 1.5 seconds. How am I going to find that? For that, I'm going to need to remember that this oscillating system, this displacement over time, is going to take the form of a sine wave. So let's draw out a little sine wave here. So when I have a sine wave, my equation for that wave is going to be that any point in my y-axis, which for this, what would be that y-axis? What would we put on the y-axis? That's going to be our displacement in x. So we're going to label the y-axis with an x. And then my x-axis, that'll be my time. So if I want to find a point that it's on in that time, first off, I need x. And it's going to be x as a function of time. I'm just going to put that there so that we know that of all the variables I'm about to write, time is the one that's going to change. And then we're going to have an amplitude that's going to determine what our maximum height is. So we could have that be a 1, maybe this is a 1, maybe this is a 5, maybe it's a 10. That's going to adjust things. And it's going to be times the sine of omega, which is our angular velocity, omega t. And then we're going to want to rewrite that to solve for frequency or period. And so let's consider what is the relationship between omega and period. So now I can either go to frequency or period. And just speaking from experience, it's going to be easier to use the frequency here. So let's do that. So I'm going to not worry about that. And then I've got 1 over f equals 2 pi over omega. So I'm going to multiply both sides by frequency and omega. F omega and f omega. So my frequency cancels out there, my omega cancels out here. I have omega being equal to 2 pi f. So I can plug that in right here. And so the equation of my wave becomes x as a function of time equals my amplitude, which I know that's 5 centimeters right there, times the sine of my frequency of 2 pi frequency, 2 pi f, times time. And that will tell me what my x is at that position. Or what my x is at that time. So I can use that. So let's start going through and solving these. We can see that these are all going to kind of build on each other. So my frequency is up first. My frequency is going to be the reciprocal of my period, which is 3.7. And when I do that, I just take 1 divided by 3.7, and that gives me a frequency of 0.27 hertz. And then my spring constant, I'm going to rewrite that down here. And then I want to get k all by itself. So the first thing I'm going to do is I'm going to divide both sides by 2 pi. So I'm going to get t over 2 pi equals the square root of m over k. And then I'm going to square both sides of this. That's going to square everything in that parentheses. And I'll end up with t squared over 4 pi squared equals m over k. And now I want to get k by itself, so I'm going to multiply both sides by k. And then I need to get k alone, so I'm going to multiply both sides by 4 pi squared over t squared. Okay, and then my k will be equal to my mass is 4 pi squared over my period squared. So I'm just going to plug those numbers in. So my mass was 40 grams, and I need that to be in kilograms. So that's going to be 0.04 kilograms times, let's put that in parentheses, times 4 times pi squared divided by, and then my period was 3.7. 3.7 squared. And I get a k value of 0.115. It's going to be newtons per meter. All right, so let's report that up here. So now the internal energy of the system, now that I have k, I can calculate that. I can just plug in my k right here, and then my x squared. This x should be 5 centimeters. Well, what am I going to use for 5 centimeters? I need that to be in meters in order to get the actual internal energy. 5 centimeters would be 0.05 meters. So I can do that over here. So got US is equal to 1/2 kx squared. This is going to be US being equal to 1/2 times 0.115 times 0.05 squared. So this is going to give me a very small number. So this is going to be 0.000144 joules, which would be, I could make this 0.144 millijoules. For reporting purposes, that would make things a little easier. Just moving around. It's going to be 0.144 millijoules. And then I want to know the maximum velocity of the mass. So let's go ahead and solve that as well. So it's going to be k being equal to 1/2 mv squared. This k, that's kinetic energy, will be 0.00144 equal to 1/2 of, and my mass is 0.0, what was it, 40? 40 grams, so 0.04 v squared. So I'm just going to divide both sides by 0.5, 0.04, which gets rid of both of those. Gives me 0.0072 equals v squared. And then I just take the square root of that, and I have my maximum velocity. Then 0.0849 meters per second is my velocity. So now we're ready to figure out the position at time equals 1.5 seconds. And in order to do that, our calculators need to be in radians. So set your calculator's mode to radians, and then we can solve this. The reason for that is we're taking the sine of this omega right here, and that is radians per second. So when I multiply that by time, I'm losing that seconds and I'm just having radians. So it's very necessary for our calculators to be in the radians mode for this equation to work. But once we have that, let's set this up. I've got x equals my amplitude times the sine of, and we're using 2 pi times my frequency times my time. So my x is what I'm looking for. My amplitude is known. My amplitude is 5 centimeters. So that's going to be 0.05, because that will still be in meters, times the sine of 2 pi, and then my frequency, that I found to be 0.27. And then my time is 1.5. So what we're really saying is, this is the equation that describes this motion. This one equation describes this motion. And I'm just saying, okay, at 1.5 seconds, where am I going to be on this graph? And I know my amplitude is 0.05. So right here, my maximum height is 5 centimeters. Down here, maximum height is going to be negative 5 centimeters. So I want to know, where am I at 1.5 seconds? And when I plug all of this into my calculator, I get 0.028, which means 2.8 centimeters. So if we look at this graph, 3.7 seconds being our period, that means right here, that's 3.7 seconds. So 1.5 seconds would be less than half of that. And so I'm probably going to be right around here. That's really what I'm looking at. So we can plug any time into this equation and find the position of that oscillator. So if I were to plug in, let's say, hey, at the period of 3.7 seconds, at 3.7 seconds, I'm right around 0. I'm very close to 0. It's 0.000314. Now at 3 seconds, I would be at negative 0.046, which would be negative 4.6 centimeters. So that would be right around here. So at 3 seconds, I'd be right there. I can keep doing this. I could plug in any value I wanted. I could say, well, what about something further out, like at 10 seconds? Where would I be at 10 seconds? I would be at a negative 0.047, so that would be a negative, it would probably be right around there, 10 seconds out. It would be at that part of the wave, 10 seconds out. So these equations for looking at a position on a waveform can be really useful because we have a lot of oscillatory motion in nature. Things like the rotation of planets or the motion of electrons or the movement in a chemical bond. Movements in chemical bonds are actually kind of bouncing back and forth a lot like a spring mass system, and they carry some internal energy. And so being able to study the internal energy of a system like this and the wave function that it produces is actually pretty close. It's a pretty good generalization for studying things like bond length and energy in chemical formulas. So that's our position there. So let's write that down, 2.8 centimeters. This is 2.8 centimeters. And then the acceleration at that point, how would I find that? Well, for that, I'm going to remember that my force of my spring is equal to kx. Well, I've got an x, I've got a k, and F net would be equal to ma, and I wouldn't have any other forces here. So I could say ma equals kx. If I know the position, I can figure out the acceleration, which is another valuable thing to know about. So I'm looking at 2.8 centimeters. So I've got 0.028, and then my k value, that is 0.115. And I'm looking for acceleration, and my mass is 40 grams, 0.04 kilograms. So I divide both sides by 0.04, getting rid of that, and that'll give me my acceleration. My acceleration is 0.0805 meters per second squared. Let's write that in. So now we've been able to answer every question on here using these equations and using the idea of this oscillatory motion, which I'm really trying to help you visualize that we have this sine wave for our motion, that we have this repeating back and forth. Now, what would this look like for a pendulum? Well, a pendulum is going to be very similar with just a few key differences. Obviously, we have a different equation for finding our period, but let's move this up a little bit to exaggerate it. But when we're looking at our internal energy, we generally keep a degree in mind for how far a pendulum is moved. But our energy isn't going to care about that angle. Our energy is going to care about this height. And so if I'm looking for the internal energy of a pendulum, I need to figure out my maximum height difference for that pendulum, and then use mgh. That would tell me that. However, I'm still going to use this same equation to figure out the position of a pendulum at relative time. For that, I can use an amplitude of a degree, because I can just say, what degree is this going to be? I can just make this axis, the x-axis, to be degrees, and that would tell me which degree I'm going on. It doesn't really matter what I put on this x-axis, I just need to be consistent. So I could say, instead of using x here, I could say theta equals my amplitude times my sine of my 2 pi frequency times my time. And that would tell me, as long as I used a degree for my amplitude, like let's say this is 15 degrees, I would put 15 in for that amplitude. That would tell me which degree I'm at. So this equation is versatile like that. I could alternatively say I'm going to keep in mind heights. So I could say height for this and then solve that for y, and then my amplitude would be my maximum height, which I would find right there. So I could find that as well. That can be a little trickier because then I've got to keep track of things in height versus angles. So with pendulums, it becomes a little more important to keep in mind which thing are you looking for? What is the problem asking for? Is it asking for height, or is it asking for an angle? However, this equation will work either way. I would still get that same sine wave.